Welcome to the demonstration of Lab 1 of CS498 Internet of Things. During this demonstration, I'll be covering part 1 and part 2, answering the specific questions in the assignment description. So let's start with part 1.
So the car is fully assembled and in working conditions. So you'll see how it drives during the demo videos of the part one, part two. So cars assembled. So there's the forward hat on top of the Raspberry Pi and powered by batteries. And I don't know if I can get a clear shot. So I have installed heat sinks over the processor since I'm doing some image processing and some heavy TensorFlow activities inside the Raspberry Pi. So yes, the car is fully assembled.
This is the setup for the part 1 demonstration. I'm going to run the script. As car moves forward, it scans for 90 degrees, 45 to right and 45 to left. And when it detects an object, it comes to stop and scans 90 to minus 90 degrees and go to the direction which does not have any obstacles. So yeah, there you see, so car comes to stop and find the direction and turn and move alongside that direction.
Yeah. This is the Python program that runs for part one. It's a very simple Python program which contains one method. So the main execution happens like this. It tries to execute the main method. If something goes wrong, the vehicle comes to a complete stop. So this main method runs on a while loop. I mean the infinite loop. In this loop, it scans, and when it comes to obstacle, it turns to directions and basically drives the vehicle. Um, we use the Pika library. So I added few changes to the library. Basically, I introduced couple of new methods. So this is one of them. So while it runs on infinite loop, in each step it scans for the angles in the front, which means like when I say angles in the front, when I define 90 degrees uh, to the moving direction, it scans 90 degrees span. So let's go into the method. So basically, when you provide 90 degrees and steps as 3, this method gives you distances for 45 degrees to right, 45 degrees to left, and the 0 degree direction. So this will provide you a list. So based on the list, you have the distance and the angle for each entry. And then based on the entries in the list, um, so we decide if there's an obstacle or not. So I have defined a ref length, which means the length that I'm looking for obstacles. If the if d is less than the ref length, which means there's an obstacle, um, and then we append -1 to the status list. If there are no obstacles, we append 2. So when you have the final status array, if there are no obstacles in the front, you should get an array 2, 2, 2. If there are any obstacles, it can be different. So if this condition is not satisfied, that means there are no obstacles in front, car can move forward. So basically the car moves forward with the speed that we have defined. But if it is not 2, 2, 2, there is an obstacle in front. So the car comes to a complete stop. And once it comes to a stop, it scans. Let me explain a bit more on this method. This is also a method that I added to a Pika library. So this method scans plus 90 to minus 90 angles in 5-degree intervals. So you'll have 36 readings after execution of one step. Of sorry, I mean execution of one time of this method. So in the distance list, you have distance and angle. So it's a reading of, um, so what is the distance that I can find an obstacle and what's the angle. So once I have the list, I iterate through the list for each record or each item, and if I can if I can find any direction or any entry in that list which obstacles are placed in more than the length of the ref length, or length is -2. So this length -2 case is very interesting because the sensor is designed to measure a certain max length. But if you cannot find obstacles within the max length that sensor has designed to measure, it gives you -2. So if you are getting if you can satisfy this condition, that means that direction is good to go. So the first direction you can find which satisfy this condition executes this block. So it picks the direction to turn. So basically, if the angle is minus, it turns left. If the angle is positive, it turns right. So this loop is continued, and obstacles are avoided during the moving of the vehicle.
This is my setup for part 2 demonstration. It has two obstacles and it should go to place that you see now beyond the red box. I'm going to run this script now. So it scans from +90 to -90 degrees first, and then it creates a map like this. In blue you see the obstacles, and in the green it's the path that the vehicle is going to follow. I have created a separate demo video for the object detection. So the Pi camera is mounted in the front. So when it comes to a stop sign, it's hold for 3 seconds and start moving on. So I'll explain how this works during the code walkthrough.
So this has some image processing and some TensorFlow and drawing maps using OpenCV. So I'll walk you through the code on how I have done this in Python. So this also the structure is similar to the part one. It tried to execute one method, and if something goes wrong, vehicle come to stop. So this part two needs some additional files, basically some models and labels for object detection, which is used by uh, car to detect objects like stop signs. So you need to pass these arguments when you run the program. And so I'm using multi-threading here. I have two additional threads. One is for updating the objects. Basically, this thread it's running for camera, so it looks at the object, it detects and updates a global object registry, and this one is to clean up the handle object. So I'll explain the concepts as we go through. Before I start going through the flow, I need to explain two methods, actually three methods that I have created. The first one is move 50. So this was taken from the assignment description. There was one method called move 25, which moves the car 2.5 centimeters. So I took the method and I made some changes and calibrations to make it move 5 centimeters in each step. So I have calibrated that on the surface that I have done the part 2 demonstration. So once this method is executed, car moves to the direction it already facing in 5 centimeters. And these two are the other two methods. This also I had to calibrate uh, per the flow. I was doing it in carpet, and I was doing the hardwood floor, and it was different. So I had to do a bit of calibrating using some trial and error methods. So by executing this method, you can turn the car 90 degrees to right, and using this, you can turn the car 90 degrees to left. All right. This is another class I wrote using the examples provided in the TensorFlow. So it's called detector. It's in here. So it's basically a class which has a model, labels, an interpreter, and a threshold. Basically, these methods were taken from the sample, and it has a method to detect objects and update a given registry. So basically, this method uses the pi camera stream, and each image is processed, and any non-objects are extracted from the image, and they are labeled and they are annotated. So this is how it works for the image. And in the part two, this is so there's a method called object detector, which uses the detector object that I created in the main method. So this method updates something called object registry. So this object registry contains the objects that are identified by the camera um, every time it detects an object. So this function is running on a separate thread rather than the main thread. And observer. So observer is actually the object detector. And there's another thing called cleaner. So whenever there's a non-object, I detect it and then I handle it. So in the move direction, you can see if there are any non-objects in the object registry. So I handle them. So this is how I handle. For each object, there's a handler. In this case, I considered only the stop sign as the non-object. So I have the non-object and the non-object handler. So basically, the handler is a simple method that comes to and stop and wait for 3 seconds. So what happens is when the car move forward, when it find a non-object in the object registry, because this object registry is a global variable and it is been updated every time that the detector threads finds a non-object in the camera feed. So whenever it detects the stop sign, it's going to be in the object registry and it will be handled accordingly. Um, and the most important thing is once you handle it, you have to just tell the car that you have already handled it. So, for example, when you see the stop sign, you stop there for 3 seconds. And since the stop sign is going to be on the camera, it's going to wait 3 more seconds. So it's going to come to a complete stop in front of stop sign. To not to let that happen, what you have to do is you have to let the car know, as I said, this is already handled. So once the stop sign is handled, it is added to another global list called already handled objects. And so if that object is already handled, we are not handling that object again. So this already handled object list is cleaned every 10 seconds. So that's how actually let me give you the right yeah, every 10 seconds. So that's why I have these two threads running and doing those tasks. And okay, so let's go to the main method. So there's a method called go. When you give coordinates, x and y coordinates, it will take the vehicle from the standing position to this position. Um, Before I go into that method, I need to explain two more concepts. So I have something called map size and the block size. This means this grid I am considering, it has 50 boxes with each like 5 by 5. So each unit, actually one unit of movement for the sky is 5 centimeters, and I'm considering 50 by 50 grid. So I'm considering the car is at the center of the x-axis, which means 25 and 0. From 25 and 0, 0 25, it goes to 2 22 position in the in there. So let's go into this method. So this runs in a while loop till it goes to the particular position. So this does the same thing. It scans for distance from 90 to minus 90 degrees in steps of 5 degree, which you will have 36 readings with distance and angle. And then these distances are converted to coordinates. So basically, if the distance is minus 2, that means there are no obstacles. And I'm also adding a buffer of 20 just to make sure the car does not collide with the obstacle. So this buffer is added. So the distance and angle is converted to x, y coordinates using these functions. Um, Basically, distance into sine angle is the x and distance into cosine angle is y. And most importantly, before that, the angle is converted into radians. Um, yes. And then the distance is normalized into the block size so that we can truly consider these coordinates are mapped within 50 by 50 map. So once I have the coordinates, I need to drive the car to the given position. So there's this method called drive. So in the drive, we use three global variables: obstacle map, path, and obstacle map image. So each of the coordinate uh, I convert them into the matrix form, because the 0 0 in a matrix and a 0 0 in a Cartesian coordinates, positions are different. So I have to convert them into basically a matrix positioning here. Um, and then once I have the obstacle map, this is basically a array of zeros and one. So if you have a non-zero coordinate um, in the map, that means there's an obstacle. So for example, if we have a coordinate 2, 2, 5, which means x position 2, y position 5, there's an obstacle. So that's how it works. And then to be extra careful, I add some paddings for obstacles, so it will give you some wiggle room between the vehicle and the object before it comes to a collision. So basically I just populate the surrounding 20 pixels or 20 blocks using once, so it knows that there are obstacles. And then once I have the obstacles map, which is 0 and 1's array, I have to convert ones to zeros and zeros to 1, because the library I'm using to get the drive path, it's called the pathfinding library with a star algorithm. It uses zeros as obstacles and ones as free spaces. So I had to invert the metric, so I simply do that using this line of code, and then using this method I get the path. So this library made my life easier, because it has a built-in algorithms. All you have to do is feed the matrix, and it gives you the path. That's it. It's simple as that. So I give it the start point and the end point based on the coordinates I pass to the method, and gives you an array of points, which later I use to plot using OpenCV. And once I have that, I create the image to show the obstacles and the path. So it's a simple RGB image with I mark different channels, with one channel with obstacles and the other channel with paths, to show that view. So I'll explain. I'll actually in the demo I showed a small window of the obstacle and the path. So that piece is resulted from this piece of code. So once I have the obstacle map, I draw it in a CV2 window to see it to see all the obstacles. So for path, we need to convert it. It's not just because, as I said, the Cartesian coordinates and the matrix indexes are different. So this method converts that matrix indexes to Cartesian coordinates and the coordinates that the vehicle can understand. And for all the entries in the path, which are like it's a point array. It going So this piece of code takes the vehicle from point to point. So this go to method takes from and to position and move the vehicle. So it's basically this method is responsible for moving the vehicle like from one block to the other. So direction is a very important factor here. So we have to keep tracks on direction. For example, if we are going towards the increasing direction of y-axis, and if the x is positive, x difference is positive, you have to turn right. And if difference is negative, you have to turn left. But if we are going the opposite direction, then this becomes actually this is swapped, right? So we have to keep track on the direction. So what I do is the initial direction I face, I mark it as direction 0 or the 360, and every time I do a turn, I update the direction. So it's a like this direction can be at any given time. It can be 0, 90, 180, 270. So the direction helps to turn the car in the right direction based on the difference. So this go-to method is very important. As I said, this helps to move the car in the right direction in the right amount. For example, let's see here. The direction is 0, which means it faces to the direction of the y-axis, the increasing side of the increased direction of the y-axis. So if 2 pos is greater than the current position, which means we have to go towards the increasing direction of x. So the car turns right and update the direction. So like that, so for the combination of each direction and the combination of the difference between the coordinates, it turns to the correct direction to move the car. And when it comes to the right position, it moves the car on the given direction by the distance. Sorry, by 5 centimeter for each direction and update the current position. Um, this method I briefly explained earlier. So this method we move the vehicle by 50 centimeters every time, and for known objects that it detects using camera, it handles them and keep moving forward. Yep, I think that's pretty much it in terms of the code. Let me see. Yep, I pretty much covered everything. Yes.